Good morning. Deep convection and the occurrence of hail and other associated extreme weather phenomena have high societal relevance across a range of impact sectors. Our application is perhaps unique in that it requires fidelity of simulations across a wide variety of parameters. So our application is actually use of WRF to predict wind turbine leading edge erosion. So leading edge erosion occurs when a hydrometeor or many hydrometeors falling strike a wind turbine blade, cutting upward through the air. That collision causes material stress, and ultimately those stresses lead to material loss, which causes loss of aerodynamic efficiency and power production. So that wind turbine leading edge erosion is a function of wind speed, because as shown on the upper right here, as wind speed increases, power production increases, but also the tip speed increases. So on large machines, the tip is moving through the air at up to 80 meters per second. Hydrometeors are falling at perhaps 10 meters per second, so that closing velocity and the kinetic energy transferred can be high. So the first dependency is on wind speed. The second is, of course, on precipitation rate. Third, on hydrometeor type. And the fourth, hydrometeor diameter. So before we conducted our WRF simulations, we developed empirical estimates of the accumulated kinetic energy transfer based on data from radar, ERA 5 for wind speeds, and assuming droplet size distributions that are Marshall-Palmer for rain or exponential for hail. When we do that for sites across the contiguous US, we find in Texas the kinetic energy transfer accumulated from hail, even though it is much less frequent, of 500 times that from rain. So hail appears to dominate the kinetic energy transfer. And we can see on the lower right panel there that the joint probabilities of wind speeds that determine the rotor speed and therefore the closing velocity, and either hail occurrence, hail diameter, or rainfall rate indicate that for a substantial fraction of the times with hail and heavy rain, the turbines are fully active, they're rotating. So our research questions are, can WRF be used to predict the likely severity of leading edge erosion so that a wind farm developer can decide whether to add additional protective measures or can choose to operate the wind turbines to avoid this damage. And of course, in addressing that question, we need to examine, does WRF exhibit fidelity versus radar or ASOS observations in terms of the marginal probabilities of the drivers of leading edge erosion, so specifically occurrence of hail, hail diameter, wind speed, and rainfall rate, and also, of course, the joint probabilities of these drivers, so the probability of hail occurring at a given wind speed and therefore rotational speed for turbines. And equally, can WRF capture the spatial variability in those joint probabilities? All of the simulations that I'll show you results from today use the Milbrandt-Yau microphysics scheme, which, as you know, is a fully double moment scheme. Our first simulations focused on this 25-day period between June and July of 2014. This is basically at the peak of a typical year of hail occurrence, but it is selected to be typical of a summer. What we saw when we did this triple nesting simulation, so the large map here shows the domain 1, which was resolved at 12 kilometers. We nested to domain 2 at 4 kilometers, turning off the convection, the cumulus scheme, and then down to 1.3 kilometers for domain 3, which is shown on the right-hand panel here, the grey dots being the location of wind turbines, and the circles being the radar that we have used in our evaluation. So what we see from that simulation is that there is a positive bias in radar reflectivity diagnosed from WRF, and also the occurrence of hail. So when hail occurs within WRF, it covers a larger area and a longer duration than estimates from radar. We see good agreement for wind speeds at 10 meters relative to point observations using sonic anemometers at ASOS stations. The correlation is about 0.63, which is consistent with previous analyses and with obviously subgrid scale variability. The precipitation cumulative density functions within 100 and 200 kilometers of radar station are fully reproduced by WRF, as is the cumulative density function of wind speeds conditionally sampled by precipitation, as shown in this panel. For the hail estimates, we're using an odds ratio as our skill metric. So an odds ratio is a function of the hit rate and the false alarm rate. For values greater than 1, we say the model is skillful. So in this panel here, we show the 9 radar stations. We showed the installed capacity of wind turbines within 100 kilometers of each radar station, the number of hours with hail as derived from radar data, and then our skill metric, our odds ratio for all hours with hail, and then the top 50%. What we can see is that with the exception of KSJT, odds ratios at all radar are above 1, and indeed greatly above 1. And if we look at the most intense events, they are well captured. So this gave us some confidence and then in the performance of WRF. So we then conducted a 3-month period over the early 3 months of 2017, so a low hail occurrence period shown here in this time series. This is hail reports per month. So we did a winter period, a low hail occurrence, and then 4 months during the summer. I should have mentioned that all of the output we're looking at here is 10 minutes, every 10 minutes. So what we see in this domain here is we've actually extended our inner domain to be 651 by 651 grid cells, so it covers wind turbine assets also in Oklahoma. On the right hand side here we have 3 panels that just show the mean wind speed during the summer months at wind turbine hub height, the accumulated rainfall during those 4 months, accumulated hail, and then the accumulated graupel. What we can see, and the magenta here dots are wind turbines. So what we can see is there are strong spatial gradients, for example, in rainfall. There are also spatial gradients in wind speed across the locations with wind turbines. There appear to be some areas where hail was more prevalent, and that graupel was relatively infrequent and of modest magnitude. What we're now working on is further evaluation of these larger sample simulations to examine whether the positive bias in reflectivity and hail that we observed in our 5-week simulation, or 25-day, simulation, is that sort of pathological for this fully double moment microphysics scheme. And of course, we're doing further evaluation of the leading edge erosion drivers, and also examining wind gusts, which is another obviously damaging parameter for fatigue loading parameter on wind turbines. We're also using them to compute kinetic energy transfer and obviously express that spatially in terms of leading edge erosion potential and the joint probability distribution parameters that I discussed earlier. Thank you for your attention.